Have you ever stopped to think about how incredible it is that doctors can see right inside you? I mean, they can map out your bones, your organs with just stunning precision, and they don't have to make a single cut. It feels a little bit like science fiction, but it's pure physics. Today, we're going to pull back the curtain on how it all works.
Okay, wow, just look at these. We're looking at a bunch of different CT scans, and they are absolutely mind-blowing. You can see the web of blood vessels, the structure of the brain. It's just amazing. This is the power of X-ray technology. It literally turns the invisible visible.
So that's the real question, isn't it? How in the world do you take a picture of a shadow, especially a shadow that's being cast by your own bones, using a beam of energy you can't even see? To really get it, we have to zoom in, like way in. All right, our first stop is right inside the machine, at the heart of what's called an X-ray tube. Honestly, the best way to think about it is as a microscopic, super-controlled particle cannon, because that's kind of what it is. This is where the magic starts. So what even are X-rays? Well, if you look at the electromagnetic spectrum, you've got radio waves on one end, then microwaves, visible light, and way, way over on the other end, past ultraviolet, you find X-rays. They have super short wavelengths and really high energy. And that high energy is the key to everything. It's what makes them ionizing radiation, which is just a fancy way of saying they pack enough of a punch to literally knock electrons right out of their atoms. So inside our particle cannon, which is really just a vacuum tube, there are two main parts. You've got the cathode, which is negatively charged. Think of that as the loading dock for the ammunition. And then you have the anode, which is positively charged. That's the target.
And the whole process happens in 4 ridiculously fast steps. First, we heat up a little wire at the cathode until it starts to boil off a cloud of electrons. Second, we apply a huge voltage, tens of thousands of volts, that acts like a giant slingshot, launching those electrons across the tube. Third, bam! Those electrons, moving at a huge fraction of the speed of light, slam into a metal target on the anode. And fourth, all the energy from that massive collision gets converted into something new. Now, here's the part that always gets me. For all that power, for all that incredible speed, this process is wildly inefficient. A whopping 99% of all that energy is just wasted as heat. That's why X-ray machines need these big, heavy-duty cooling systems. Only that tiny 1% sliver of energy actually becomes what we want, X-rays. And get this, even that little 1% isn't just one thing. It's actually a mix of 2 different kinds of X-rays. First, you have what's called braking radiation. Imagine one of our electrons zipping past an atom's nucleus. The nucleus kind of tugs on it, causing it to hit the brakes and swerve. The energy it loses in that swerve gets shot out as an X-ray. The other kind is characteristic radiation, which is more like a direct hit. The incoming electron smacks another electron right out of its orbit. Then, an electron from a higher orbit drops down to fill the empty spot. And when it does, poof, it releases an X-ray with a very specific characteristic energy. Okay, so we've fired our particle cannon, we've made X-rays. Now for the big question. How does a beam of these things turn into that detailed picture we saw? Well, for that, we need to play a little game of atomic billiards. On the left, we've got a perfectly happy, stable atom. Everything is in its right place. But on the right, here comes an X-ray photon. Acting like a cue ball, it comes screaming in and just whack! Knocks one of the atom's electrons clean out of orbit. That is the ionization we were talking about. Ionization is really the fundamental interaction here. That X-ray has so much energy that it can break the glue holding an electron to its atom. So it kicks the electron out, leaving behind an atom that now has a positive charge, an ion. In the process, the X-ray photon itself is either absorbed or it gets scattered and bounces off in a new direction. So here's the aha moment. Not all atoms are the same in this billiards game. Denser materials, like the calcium in your bones, are made of bigger atoms with more protons and electrons. That makes them a much bigger target, much more likely to stop an X-ray photon. But your soft tissues, like muscle or fat, they're less dense, so the X-rays tend to zip right through them. The final image is just a map of what got through and what didn't. It's a shadowgram. The bright white parts are bone, where X-rays were stopped, and the darker parts are where they passed right through. But we can actually be a lot smarter about this. That raw beam of X-rays coming out of the tube isn't perfect. It turns out we can refine it, we can clean it up to get much better images, and, this is super important, to make the whole thing safer for the patient. This brings up a really good question. Remember how we get a whole mix of different X-ray energies? Are all of them actually useful for making the picture?
And the answer is a big, clear no. The low energy or soft X-rays are actually just trouble. They don't have enough oomph to make it all the way through you to the detector, so they don't help the image at all. Even worse, they just get absorbed by your body, which increases the radiation dose for no reason. And on top of that, they can cause scatter that just fogs up the final picture. They're all downside, no upside.
So the solution is actually pretty elegant. It's called filtration. We literally just stick a thin sheet of aluminum in the beam's path. It acts like a bouncer at a club, right? It blocks all the weak, low-energy X-rays, but it lets the useful, high-energy ones pass right on through. This process is called hardening the beam because it raises the average energy of the beam that makes it through. And you can see how well it works right here in this table. This half-value layer, or HVL, is just a way of measuring the penetrating power of the beam. And look what happens. As we add more aluminum filtration, the HVL number goes up and up. That's proof that our beam is getting tougher and way more effective for creating a nice, clean image.
So, okay, we started with a basic shadow. We figured out how to filter the beam to make it cleaner and safer. So what's next? Well, the future of this technology is about moving beyond just black and white and into a full spectrum of color. You can think of a regular CT scanner as being kind of colorblind. It can tell you that the beam got weaker, but it has no idea which X-ray energies got absorbed the most. It just sees in shade of gray. But this new rainbow CT technology is different. It acts more like a prism. It can actually separate out the different energy levels, which lets it identify specific materials based on their unique energy signature. It can see in color. So how does it do that? Well, instead of that one simple aluminum filter, it uses a whole series of really advanced filters. Each one is engineered to only let a very specific, very narrow slice of the X-ray energy spectrum through. So the machine takes a quick picture through one filter, then another, then another. The computer then combines all of those energy-specific images to create one super rich, color-coded map. It's literally like giving the scanner color vision. And this right here is what it looks like. This isn't a simulation, it's a real image from one of these experimental scanners. It's showing you only the information from one of those narrow energy colors. Now just imagine combining several images like this, each from a different energy window. You can build a much, much more detailed picture of what's really happening inside the body. Which brings us to the final thought. We've journeyed from a simple shadow to a smarter, filtered beam, all the way to a full color spectral image. The ability to not just see density, but to actually identify specific materials inside the body, that is a massive leap forward. It's a whole new frontier. And it really makes you wonder, right? What medical mysteries could we finally solve now that we have X-ray color vision?